Hello, everyone. My name is Jay Lago. This presentation will be about a new model we've developed on generative probabilistic transformers for ionospheric forecasting. So first and foremost, let me define what we mean when we say the ionosphere. This is a region of Earth's atmosphere that starts at roughly 60 kilometers in altitude and extends up through about 1,000. It's characterized by these distinct layers known as the D, E, and F region. And it has this very strong diurnal cycle due to the ionizing effects of the solar radiation. Now, its dynamics are especially difficult to predict since it is coupled into this larger constellation of geospace dynamical systems. Thus, kind of motivates a more data-driven approach rather than attempting to solve all of the governing equations for all these systems. So to that end, one of the key parameters of the ionosphere that we can collect data on is what's known as the peak of the plasma density profile at a given location. And we call this peak FOF2. And here we're showing several time series of FOF2 at different locations over the last couple of decades, with Colorado on top, Guam in the middle, and Alaska on bottom. And what we see is that there are very real differences in the behavior of this parameter at different locations, specifically different latitudes. And so that's something that we want to incorporate into our model. To do this, we obtain a geographically diverse set of both training and test sets. And so we want to build a model that generalizes to new locations. So we collect data from a large number of sounding stations that can measure the FOF2 parameter. And we hold some of them out during training in order to test our generalizability. So each dot here represents a location where data was collected, and the relative size of the markers indicates the amount of data over the last 23 years that was obtained. So note that our test data come from distinct geographic locations. So the model we've developed is an encoder-decoder model using the transformer architecture of Vaswani et al. Now, the transformer was originally developed in the context of natural language processing, where the inputs would be a sentence or paragraph of text, and the model would predict the next token or word in a sequential fashion. So we've modified this instead to generate a one-shot prediction over a fixed time horizon of the FOF2 parameter. Our model consists of two main attention head blocks, the encoder, which learns a dynamic set of weights over a past history of covariates. In this case, it's ingesting, in addition to the FOF2 parameter, some observed covariates that include solar zenith angle, KP and AP index, which are geomagnetic indicators, sunspot number, and F10.7 centimeter flux, which are solar indicators. Then the decoder block ingests only what is known about the future. In this case, that would be solar zenith angle, which is a very easily computable value for any geographic location and time. The output of the model then is a time series of location and scale parameters that are used to generate a probabilistic forecast using normally distributed errors. So this architecture can be visualized more easily with one of our diagnostic plots used during training, where we have this vertical black line that indicates the transition from past to future. And so the encoder of the model receives a time series of the observed FOF2 data here on top, as well as the observed covariates here on bottom. Meanwhile, the decoder receives only the solar zenith angle over the course of the future prediction time, and then learns to integrate all of the information from the encoder with itself to produce this time series of distributions of FOF2 over the forecast period. So the result of this, of training this model on 2 decades worth of data from many geographically different sounding stations, is a model that can generalize to completely new locations, as seen here in some of our test data. So note that the forecasts here not only accurately predict the median of the FOF2 seen in red, but it's also able to dynamically adjust the forecast, the expected error of the forecast based solely on the previously observed data. And so with that, I will leave you with some acknowledgements for my collaborators, and thank you for listening to my talk.